last time, we derived rho k equals I equals 1 to p 3 of I rho k minus I, and this is for an ARP model. Of course, the stationarity conditions apply in the weak sense. So our objective primarily is to estimate the values of phi. All we've done thus far is to understand the model. We have not estimated using an exact series, but all of statistics is based on that. So how are we going to fit a model to estimate those phis? The moment we have a model, we can make a prediction, right? Just like regression. You have a bunch of x and y values, you fit a regression model, and once you have the model, you can plug in values and make predictions, correct? So, that is our goal. Hopefully we have a good understanding of the models, right? In terms of the definition, in terms of characteristic equation, all that fun stuff. What is Yule-Walker estimation? It is a simple technique that we use to estimate the values of the coefficients so we can fit the model. Did we bring our calculator? If I start with an AR1 model, I'll change the ink. I can start with rho 1, which would give me some I equals 1 to 1. 3i rho 1 minus I. I can expand the sum out, and I'd end up getting phi1 rho 0. So rho 1 would equal phi1 times rho 0. But what is the value of rho 0? Autocorrelation when the lag is 0. If the lag is 1, whatever I'm measuring today is related to yesterday, right? Going backwards. But if the lag is 0, whatever I'm measuring today is correlated with today. That's it. What is rho 0?
It's usually 1.
1. Yeah, regressing onto yourself. So that would be 1. So rho 1 is simply phi1. That should come back to you from when we did ACF using R. I obtained the ACF plot and I said, oh, look at the value of the ACF when lag equals 1. That equals whatever we had in the model. And it works for AR1, it is not going to work for other cases. Great, I'll show you, I'm planning on showing you doing some art. So, good, AR1, easy. AR2. AR2 model, XD is phi1, XD minus 1, phi2, XD minus 2, plus epsilon, epsilon 2%, AT, same habit. In my book, I'll be using XD and epsilon C, made up my mind. So we have two coefficients to fit, phi1 and phi2. And how do we get those values? We are going to make use of the autocorrelation function, which is why I said time series autocorrelation function is the most important function. In time series, the most important function would be the autocorrelation function. Going back to our expansion that we had, rho 1 and k is 1. I have some I equals 1 to what is the maximum index that I will get to? 2. Bi and rho 1 minus I. Let's go ahead and expand this out. When I is 1, we have phi1, rho 1 minus 1, 0. When I is 2, I'd have phi2, 1 minus 2, rho negative 1. Or rho negative 1 and rho positive 1 are one and the same, right? We'll put that as rho 1. Rho naught is just 1, so I'm going to get rid of that. So that is my first equation. Second, rho 2. So I equals 1 to 2. Bi rho 2 minus I. When I is 1, we will have phi1, rho 1, 2 minus 1. When I is 2, phi2, 2 minus 2, rho 0. But rho 0 is just 1. So phi1, rho 1 plus 2 would equal rho 2. Good so far. Two equations, equation 1, equation 2, two unknowns, and we've got to find the solution. What do we use? Algebra. Works. First equation, rho 1 is equal to phi1 plus phi2 rho 1. Rho 2 is phi1 rho 1 plus phi2. That is a linear system of equations. Agreed. I can do algebra and solve, but there has to be an easier way, right? What is the easier way? Using a matrix. Time to connect the dots. I'm going to write this as rho 1, rho 2, column vector. We do know matrix multiplication.
Yeah.
Okay, I'll just get over it. I'll go over it. So, phi1, 1, rho 1, rho 1, 1, phi1, phi2. When I teach matrices and matrix multiplication, I simply tell my students, well, you just run on top of a cliff and jump. Run, jump, and you just add as you are jumping, not knowing or knowing very well that you're going to die when you hit the ground, but you're still at it. So run, jump, so 1 times v1 plus row 1 times v2. That equation. Run, jump, row 1 times v1 and 1 times v2. That's so run, jump. Easier way to remember. Okay, I'm going to give this a notation. I'll follow the notation. I was looking at it last night because I quite E2, 3, row.
That's a P2 or row 2?
This is P.
Okay.
Uppercase. I wonder what's uppercase row. I need to look that up. Good. So row is simply a column vector containing the autocorrelations and coefficients vector, and that is our matrix. To find the solution, you multiply both sides by the inverse of the matrix theta. So we don't know matrices. Easier way to remember 1/2 times 2 is 1, right? So 1/2 is simply 2 raised to negative 1. Same logic, but we are extending it to a higher dimension. So those two would go away, and you'd simply have B that is simply the inverse of P2 multiplied by rho. That is the theoretical expression. In practice, how would that translate? Well, in practice, we have an observed series. We have estimates of rho, right? Whatever the ACF is giving us is not the true value. We have seen that in the simulation. I use a specific fee and I know what the theoretical rho will be, but I'm not going to get the exact value. I'm going to get an approximation. So I can put that formally as rho hat. In statistics, an estimator always has a hat. There's a beat going on. And my friends ask me, why are you wearing a hat today? I simply say, I feel like an estimator. I still wonder why they are my friends. Same fee hat. If you go to the library and pick an undergraduate, by undergraduate I mean lower level starts book, rho, the correlation coefficient will be denoted by the letter lowercase r. No lowercase r. One and the same. Similar to how we denote mu, estimate of mu as x bar, but estimate of mu can also be written as mu hat. because it is an estimate. So estimate of the autocorrelations that we are going to get from the observed series, estimate of the coefficients, and we are set. Here's a question, let's see if you can connect the dots. Look at that matrix. Maybe 2-3 weeks ago, before the first exam, I said there is a condition for an autocovariance matrix or an autocorrelation matrix. What is that condition? Yeah.
Has to be positive, semi-definite.
It's positive semi-definite, and there are multiple ways to check that. One, positive semi-definite, and that happens if matrix is square, obviously square. If it's symmetric, so we have a symmetric positive semi-definite matrix, and positive semi-definite matrix is a condition from a long time ago for a series to be stationary, correct? We both have stationarity, root matrix conditions, we wrote conditions on V1, V2. So positive semi-definite matrix, square, symmetric, all that is going to help us invert the matrix. If I can invert the matrix, I have a solution. Agreed? In other words, I have the estimates for the coefficients. Good. However, if the model is not stationary, in other words, the observed series is not stationary, you are not going to have a positive semi-definite matrix here. Is it going to be symmetric? Yes. Is it going to be positive semi-definite? Probably not. You are going to end up having some issues going on here, which will prevent you from inverting that. I take that back. It is going to be positive semi-definite, but you just will not be able to invert it. Good? Autocovariance always positive semi-definite. So sure, you'd have positive semi-definite matrix, but it will fail right here. You will not be able to invert. If you're not able to invert, no matter what ACF values you have, useless, correct? Without that, I can't find that estimate. So, which is why we need the stationarity condition with AR models. Good? Okay, here's a simple example. And we will use R to estimate or to see this in action. AR to Yule-Walker. Suppose I observe some series XT and I got the autocorrelation function. So I have the estimates for autocorrelation. So row hat. Here's a question. What do we expect the autocorrelations to look like for an AR model?
Well, I'm expecting to be between 0 and 1, but then
Definitely.
like decreasing by.
Very good. So ideal case, right? Practically speaking, All we are saying is, if you are up to date and actually go backwards, the correlation better decrease. You can't have the same correlation. It can't suddenly go up. That's silly. If something is following a stationary pattern, as you go backwards, the correlation will decrease. That should remind you of a function.
Oh, I was gonna say ACF,
No, the type of function, right? What function has the shape? Hence, we start at 1. Then start at 1 and it goes like this. Domain 0 to infinity. Hint, it's got something to do with one of the letters in the alphabet. Exponential. Great. A continuous function would be an exponential. So that's passing is what we call a damped exponential. Why damped? The autocorrelation is getting suppressed as you go back in time. Exponential, damped exponential. That is what I'm expecting to get if it's an AR2 model. So I am going to start with 0.64, the next value perhaps negative 0.16. Mind you, that doesn't correspond to this. This is just a side note so you can understand autocorrelation. Good.
Doesn't that have to be between 0 and 1?
Yes.
Why you have a negative? -0.
Autocorrelation can be negative. So it's a great question though. Exponential functions don't take negative values. However, when we say damped exponential, we are simply referring to the shape. We're not saying it is an exponential function. If you want to kind of relate to formal exponential functions, let's say I have that exponential because the lowest value that you can get is -1. So if that corresponds to e raised x, negative e raised x. That makes sense. Okay. Great question. We have seen a shape like that, or a picture like that before with an AR model. We might see it today. Let's see. So P2 would simply be 1, row 1, which is 0.64, 0.64, minus 0.16. So we've got a estimate of row, which is row hat. We have P2. We can find an estimate for the fees, which is simply the inverse of P2 multiplied by row hat. So grab your calculator.
This page does they come with it?
So it has to be 1 and not negative 0.16. I'm thinking like 1 step ahead. When we get to P3, you would see row 2 pop up there. Okay.
I'm just going to use Total. And see if you can narrow
Okay, so in your calculator, we can't perform matrix operations. So we just have to define the matrices. So press second and the X inverse button. And you have a bunch of named matrices. We just have to define them. So off to edit, select one, and we can define the matrix B2. Let's start with B2. B2 is a 2 by 2 matrix. 2 rows, 2 columns. So 2, 2. Put in the values 1.64, 0.64, 1. Good. Back to matrix. We have to specify the row hat vector, which is also a matrix. So 2. No, didn't need to do that. Have to exit that. Then go back to matrix. Over to edit. 2. Row hat has 2 rows, 1 column. So 2 rows, 1 column. 0.64. Second value, negative 0.16. Good. So we have entered the matrix B2, we've entered the matrix vector row. The coefficient vector estimated values is simply the inverse of P multiplied by row, or inverse of P2 multiplied by the row hat vector. So back to matrix. I saved P2 in A, so select 1. With the calculator, it's very easy. You simply have to press X inverse. You'll see the inverse button and follow it up by second matrix option 2. Good. So here, A inverse B is nothing but P2 multiplied by row hat. Do keep in mind you cannot switch the order. You will get a dimension error. So hit enter. Those are the values that I get. I end up getting 1.257 and minus 0.9647. Good. The estimated vector is 1.28, that's rounded to 2 decimal places, and 0.96 with a negative. So that simply implies the estimate for phi 1 is 1.28, estimate for phi 2 is negative 0.96. Good. Great. Okay, so we've got the estimates, and one of the values is 1.28, and you might immediately start to wonder, is it stationary? Because if we looked at an AR one, the value of phi has to be between -1 and 1, not equal to 0. The phase here, at least one of them, is 1.28, the other close to 1, and you might wonder, well, is this stationary? I don't have a clue, but we will verify soon. I'm going to write the fitted model. This is the estimated model for the series that gave us that, or row vector, estimated row vector. So xt equals 1.28 xt minus 1 goes minus 0.96 xt minus 2. And do keep in mind, you don't put plus epsilon t. Good. This is the estimated model. We have accounted for the noise already in terms of the variance. Good. Or estimated variance. So that is our model, and we got that simply by using autocorrelation. Good. Think one more case, and we can generalize and switch to R. Erase. How does the basis transform to an AR3? Again, it's K. It is going to start with rho K. Rho K is sum I equals to 1 to what is the maximum value? 3. Phi and rho K minus I. In the previous problem, I stopped at row 2. Agreed. Why?
Going back 3 times 7. 2. Yeah, so.
AR2 model, if you know that you have an AR2 model by looking at the ACF plot, why go back more than 2 steps? So here, 3 steps, and we stop. Row 1 would be phi 1. Open K equals 1 and expand after. So when I is 1, I would end up getting phi 1, row 0, phi 2, row 1 minus 2, which is minus 1, plus phi 3 times row 1 minus 3, get minus 2. Good. Row 2. So I equals 1 to 3, phi I, row 2 minus I, phi 1, 2 minus 1, 1, phi 2, 2 minus 2, 0, phi 3, 2 minus 3, negative 1. One more case. Row 3. Sum I equals 1 to 3. Phi I, row 3 minus I. When I is 1, we'll have phi 1. 3 minus 1, row 2. Phi 2, row 3 minus 2, I get row 1. And lastly, phi 3, row 3 minus 2, row 1. 2, 0, 1. Good.
Why is it go 0 then 1? Why would it be 1 to 0?
Come again.
Why would it be row 2, row 0, row 1 rather than row 2, row 1, row 0?
Okay. Three equations, 3 unknowns, we can solve. -1, -2, the same as 1, 2. We know that, so let's go ahead and replace that to row 1, row 2. Run, jump. Left hand side, I have row 1, row 2, row 3. The coefficient vector, phi1, phi2, phi3. Ready? Phi1, phi2, phi3. So row naught is just 1. So 1, row 1, row 2. Run, jump. 1 times phi1 plus row 1 times phi2 plus row 2 times phi3, and that is the equation. Good. Same logic. Phi1, phi2, phi3 comes out. I'll have row 1, row 0, and row -1. So row 1. Row 0 is simply 1, and I'll end up having row 1. Good. Last case, row 2, row 1, row 0. It's just 1. It's a matrix symmetric.
Yes.
Great. It is going to be positive semi-definite. This is P3. And if I want to estimate the coefficients, phi would be P3 inverse multiplied by rho. I'm putting hats to indicate that I will be using rows from a series that I observed, and based on what I observed, I get estimate of P. Good. How do we extend this to, AR4, AR5, AR6? As I mentioned a while ago, typically, I would be surprised if someone would fit an AR27 more. So you just can't do it. Because it's silly. Why would you predict something going all the way back to 27 days? Well, perhaps you can change the series and you can measure it over a month. Then you could go one step backwards. Right? That makes better sense. But we have to take an average rule. Let's not get into that. So usually these matrices don't get too large in time series. But single thing, they can get pretty large. So for ARP, this is simply going to reduce to inverse of matrix B multiplied by row hat I'm pressing a subscript of P to indicate the order of the model. Good. What will it look like? How do I write this model? It is pretty easy. Remember, a while ago I said I minus j is something that you've got to keep in mind in this class. In linear algebra and matrix analysis, we indicate row index by I, column by j. If I go with, let's see, what should the index be? Okay, 1, 2, 3, starting at 1, right? I is 1, j is 1, 1 minus 1, 0, raised up 0, 1, 2 minus 1, 1, 3 minus 1, 2. Yes? Back down here, column 1, row 2, 2 minus 1, 1, 2 minus 2, 0, 2 minus 3, negative 1. But we know negative 1 is the same as positive. So pretty much you can, use a program to fill this matrix easily with a for loop, or if you are an efficient programmer, without a for loop. Good. Are we clear? So 3 by 3 matrix would end up becoming a P by P matrix. Good. Okay. So we are going to use R and see if the arbitrary rows that I fit and the coefficients that I fit, would they correspond to a series in practice? Let's see. I have no idea.